So let's continue with some properties of matrix algebra. We'll look at two theorems here. First theorem is the properties of matrix addition and scalar multiplication, and the second theorem is the properties of matrix multiplication. And just notation here, all the uppercase letters are matrices and the lowercase letters are constants or scalars, real numbers. And whenever you see the I here, this I is the square matrix, named the identity matrix, of ones on the diagonal and zeros everywhere else. I is this identity matrix. The 2 by 2 variant is this one, 3 by 3, this one, and then etc. And it's always a square matrix. Okay, so a lot of these properties are sort of properties that you would see with real numbers. So the commutative property, the associative property, adding zero, etc. And the same with properties of matrix multiplication. So what's interesting is not the properties that are true, which are these ones, but the things that are omitted from this list. In particular, the one obvious omission, if you know the different properties of real numbers, is the commutative property of multiplication, which is AB equals BA. This is true for multiplication of real numbers, but it turns out to be not true in general for matrices. So we're going to look at a couple examples and show what sort of consequences there are with this omission. So let's let A equal 1, 0, 1, 0, and B be 0, 0, 3, 3. And let's compute the product two ways. So we'll compute the product of AB, and then we'll compute the product of BA. And we'll see that they aren't equal. And maybe you can see this already if you're familiar with matrix multiplication. So, like I said before, we take the first row and the first column, we multiply them, that'll be the first element of my product. So 1 times 0, 0 times 3, that's 0. And you can see that same thing happens when I take the first row and the second column. So that will give me 0 again. Let's use black here. And then if I repeat it with this second row, same entries. So this just results in the zero matrix. The product of A and B is the zero matrix. Furthermore, if I compute this product, so doing the same thing here, first row, first column, I get 0. And I do it again with the second column, I get 0. And then I do second row, first column, I'll get 6. And second row, last column, I'll get 0. And these are not equal, which justifies my earlier statement about this not being true in general. It's not true for these, so it can't be true in general. And there's another strange consequence of this, and that is you can have a product of things that equals 0, and that does not imply that one of the two pieces is 0. So AB equals 0 does not imply that A equals 0 or B equals 0. This is a feature of real numbers, but it's not a feature of matrices. And that makes matrix algebra fundamentally different than real number algebra. Let's look at another example. Let's let C be 0, 0, 6, 0 and show that though B does not equal C, BA does equal CA. All right, and we're using the B and A matrices from above. So maybe you can pause the video here and work on this problem for a couple minutes, and then start it up again when you've demonstrated what this problem is asking you to demonstrate. Okay, so we need to compute these two products. It's obvious that B does not equal C. Just looking at them, those are different matrices. 0, 0, 3, 3, and 0, 0, 6, 0 are different numbers, and involve different numbers, excuse me. However, if I compute BA, well, I did that already. That's 0, 0, 6, 0. And if I compute CA, well, let's do it. So we have 0, 0, 6, 0 times 1, 0, 1, 0. First row, first column is 0. First row, second column is 0. Second row, first column is 6. Second row, second column is 0. And these do match. So BA, these equal CA. These are equal. And this is another strange result. It's actually kind of tied in with these other results. But if you have BA equals CA, it does not follow that B equals C. You can't cancel the A. You can't cancel A from both sides. Even though A is not the 0. It's not 0. It's not a 0. So typically you can't cancel a number if it's 0, but otherwise you can cancel it. But in this case you can't. You can't cancel A from both sides even though A is not 0. And by 0 I mean the 0 matrix. So this once again makes matrix algebra very tricky. You have to be very careful about the rules that you bring over from real numbers. Cancellation, not allowed. Product equals 0 implies the two pieces, one of the two pieces is 0, not allowed. And commuting multiplication, that's not allowed. All right, let's look at one more example. And this is an open question. So can you find an A that's non-zero such that A squared equals 0? And this is once again a variant of the AB equals 0, but the two pieces are not 0. So we want a non-zero matrix that when we square it we get 0. And I want you to pause the video again, try this, and see if you can't figure it out. Okay, so there's lots of A's that have this property. The easiest A that I can find that has this property is this one. This is a 2 by 2 A. 0, 1, 0, 0. If you multiply this matrix by itself, square it, you see that that 1 can never hit the other one because it's this row times this column. That's going to result in 0. First row, second column, that's going to result in 0. And then you have a 0 row times anything, that's just going to be 0. So we have A is not 0, but its square is 0.